Okay, good afternoon, everyone. Thanks for joining today's seminar. We are very pleased to have Shira Chapman from Ben Gurion University. She's going to talk about on holographic flow geometries. Over to you, Shira.
All right, thanks a lot. So hi everyone. Thanks a lot for inviting me to give this seminar. Yeah, as always, I learn a lot from giving talks. So especially from the questions of the audience. So you should feel free to interrupt me at any time. The slides are built in such a way that I don't actually have to finish them. You will get the point at an earlier point than the end. So you should feel free to stop me at any time. Right, so today I'm going to talk about a type of geometries which allows us to study the CHEP-th horizon from a holographic perspective. And in particular, I will focus on how tools of quantum information can be used to better understand the CHEP-th horizon within this new holographic framework. And this is going to be based on a paper which we put out a couple months ago together with Damian Galante, with this guy over here. You can see my cursor, right? Yes. So yes. With Damian Galante, with this guy over here, who is now a Hawking Fellow in King's College in London, and Eric David Kramer, who is a postdoc at the Hebrew University in Jerusalem. Right. Okay. And one thing that I should say before I start my talk is actually that, I'm not pressing the right thing. Let's see. Yes. One thing that I should say before I start my talk is that a lot of the beautiful graphics was actually designed by Damian. So he's the architect behind all the beautiful graphics. All right, so here's an outline of my talk. So I will start by a short review of the CHEP-th spacetime and the cosmological horizon, followed by a comparison between black hole horizons and cosmological event horizons. Then the second part of the talk, I will present these flow geometries, which allows us to study the CHEP-th holographically. And finally, I will focus on the quantum information aspects. So I will talk about computational complexity in flow geometries. And of course, I will present a number of future directions and summarize. So here's the first part. First part is just this essentially review of the CHEP-th and the cosmological horizon. So first, what is the CHEP-th space? I guess many of you know. The CHEP-th space is essentially a maximally symmetric solution to Einstein equations with a positive cosmological constant, which can be realized or embedded as a hypersurface in a flat D+1 dimensional Minkowski space, and is simply the hyperboloid. Now, there are various set of coordinates that describe it, but for example, global coordinates looks like that. And you can see in them one of the features, which is that the CHEP-th universe expands infinitely towards the future. And the reason that we are very interested in the CHEP-th space is that both the early universe during inflation and the current area of our universe, or the late limit, at least approximately, are very well described by the CHEP-th space. Now, the CHEP-th space has a number of geometric properties, and one of them is that it has a cosmological horizon, and that's due to the rapid expansion. So essentially, there are parts of space which are moving away from us faster than the speed of light, and as a consequence, there are certain regions of space which are outside the causal contact with a given observer. So that's the Penrose diagram of the CHEP-th space. It looks a lot like the Penrose diagram of a black hole. We live over here on the South Pole, for example, on what we would call R = 0. And there is a cosmological horizon at some finite value of the radial coordinate. So this blue region over here is actually called the static patch, and it can be described by the following static patch coordinates. And as I said, there is a horizon at R = L that we call the cosmological event horizon. And of course, if we continue beyond this horizon, we are going to look at the expanding space and reach this R goes to infinity line, which is often dubbed Scri+. Now, unlike in the black hole case, space-time inside the static patch is finite. Meaning that if I look at the same triangle in the diagram of a black hole in ATS, this part would usually be infinite. And space here expands toward the horizon rather than in the black hole's case where it shrinks towards the horizon. So let's make a comparison just to keep in mind some similar and some different properties between black hole horizons and cosmological horizons. So first, the similarities. So both, as we said, black holes and cosmological horizons share some similar features. For example, they have a similar causal structure in the sense that light cannot escape from within the horizon, etc. They both have Rindler type behavior close to the horizon, including a certain associated temperature. And they both have an entropy, and here I mean entropy in terms of the second law of or the first law of thermodynamics applied to gravity, nothing deeper, not the counting of degrees of freedom, but they both have an entropy given by their area. But there are also many differences. So before I start talking about how to do holography for the cosmological horizon, I want to discuss two simple features of the geometry that are remarkably different between the two cases, just to give a feeling. Of course, there are many differences. The first one has to do with what happens when you send some energy into the horizon. So that's the issue of shock waves. And the second difference will have to do with geodesics. How do space like geodesic look in these geometries? So shockwave first. When I send a shockwave into a black hole, the black hole horizon increases inside, and essentially if the energy is positive of what I send into the horizon, then I, in a sense, close the wormhole. I see less space after I send this object into the horizon. For the cosmological horizon, it's the other way around. So when I send something into the cosmological horizon, the cosmological horizon reclines and shows up a new portion of space. And that can be very easily explained from an entropy perspective. So if I throw things away, I lose information, and when I lose information, the entropy increases, so the area of the horizon increases. So now that's in de Sitter. So in de Sitter, as I said, positive energy perturbation connects otherwise disconnected regions of space-time, while in black holes in ADS, this is only possible with negative energy shocks, and that's all this story of the traversable wormholes. So that's one difference. And the second difference has to do with, of course, second out of many, has to do with how space like geodesics look. So let's, for simplicity, consider a two-dimensional geometry, a two-dimensional de Sitter, or a two-dimensional black hole, and with the following metrics, so essentially minus FFR, dt squared plus dr squared over FFR with the following blackening factors. Now, I'm going to look at space like geodesics, which are between like these points in the Penrose diagram, so between, for the black holes, between the two boundaries of ADS, and for the de Sitter between the north and south pole, so between the two wall lines of an observer. And I will tell you how the length of these geodesics depends on the times. And just to mention before I do that is that there is an isometry in this geometry. So if I move one of the points down and the other one up, the length of the geodesic will remain the same. And so without loss of generality, it's enough to consider only symmetric geodesic. We can always use this as this isometry to move the geodesics to be at equal times on the two boundaries. Okay, so now the procedure is pretty standard. So to find geodesics in this space-time, we extremize the length, in this case written in terms of light coordinate v and the radial coordinate r. We define a conserved momentum, and we use this conserved momentum to rewrite both the length of the geodesic and the boundary time where the geodesic hits the boundary. So they would both depend on this conserved momentum, and so we would have a parametric plot of the length of the geodesic as a function of time. Now in 2D, things are simple enough that we can really solve everything analytically, and we can show how the length of the geodesic depends on time by an analytic expression. So here is now a comparison between what happens in DS and what happens in ADS. So in ADS, these are the geodesics. Essentially, they are very simple. There is a cutoff that we put so that things don't diverge at some value RP, boundary radius. And the length of geodesics looks like that. So it's essentially something like log of cosh, such that at late times, when t is large, the cosh is dominated by an exponent, and this essentially goes linearly with time. And this linear growth is very often assigned to the fact or associated with the fact that the theory is chaotic. So it's often said that this, that having a linear growth of this space-like geodesics is a signature of chaos, of a chaotic system. Now in De Sitter, it turns out that something quite special happens. So first, all the geodesics have exactly the same length. They're all of just length pi. But actually, geodesics don't exist between every 2 points on the boundary. They only exist between points at opposite times. So if we force it to be symmetric geodesic only at t equals 0. And that's essentially what we find. So not all points along the wall line of an observer are connected by geodesics. Only points with opposite times are connected by geodesics. There is a one parameter family of them, but all have the same length. And at some point, the geodesic become null and touch a future or past infinity. And after this point, there are no more real space-like geodesics. Geodesics become complex. So this in itself is just a curiosity to see how different the geodesics are, but these properties of how geodesics, space-like geodesics behave in De Sitter is going to be later important. So just remember this kind of diamond or element of how space-like geodesics behave in De Sitter will be later important when we talk about flow geometries and how to essentially study De Sitter holographically.
Hi, Shira, I have one question. So the linear growth of this length that you have mentioned is only true for after some time or scrambling time, something that we usually refer, or is it just from the starting?
Shira, you're muted. Shira, you're muted.
Oops, sorry. Yes, so I'm saying you're absolutely right. This happens after times of the order of the inverse temperature that you get a linear growth. And at early times you have, in this case, quadratic growth, but that's true, it's a late time effect.
Okay, thanks.
All right, so we say, so that's the second difference. Geodesics in De Sitter behave very differently from those in black holes. All right, and here's a summary of the difference. Positive energy shock waves, quote unquote, open the wormhole, and geodesics in De Sitter behave differently compared to those in black holes. All right, so this was just like essentially an elaborate review of De Sitter with some chunks that I will need next. Now let me move to the, let's say, the main new technology, which is how to do holography in De Sitter space from flow geometries. So first, well, why would I want to do that? So the reason I might want to do holography for the sitter is that it has proven very useful for black hole horizons, actually, in the context of ADS-CHEP-th. So we know that ADS-CHEP-th has been an extremely powerful tool to understand black hole horizon using the boundary perspective. And this has been done from like using many aspects of it, including thermodynamics, hydrodynamics, entanglement entropy, thermalization, quantum chaos, and more recently, quantum computational complexity. But despite the progress with black hole, the ADS-CHEP-th toolkit was not extensively used for the cosmological event horizon. And you may ask why? Why is this so? I mean, there were a few proposals, but all have some disadvantages, which I will explain now. So why is it so difficult to do holography for the sitter? The straightforward reason is that we don't have a time-like boundary in the sitter, like in ADS, where to anchor the boundary observable. The word line of the observer, meaning the R equals 0, is not a boundary, it's just a point on the sphere. And scribe plus, on the other hand, is a boundary, but it's not time-like. So the theory that lives there is not exactly what we would want from a standard dual with the time direction. And so an idea that came out quite a while ago already was, I mean, that's a very natural thing to think about, is what if we embed a patch of the sitter space inside ADS? In this case, we would have a cosmological horizon to study in the interior and an ADS boundary with a reasonable standard dual with the time direction to probe this cosmological horizon. So this was studied actually quite early on, not trying to do holography, but trying to embed the sitter in Minkowski under, you know, the title of "Can we build a universe in a lab?" And then later on in the context of holography that I will discuss in a bit. But it turns out that that's extremely difficult. Why is that difficult? There are some no-go theorems that I will describe now. But of course, I will also describe how to bypass them. But the no-go theorems usually go like that. So they say, let's consider a metric with a blackening factor f of r and some size of the sphere, g of r, and assume that the total matter stress tensor obeys the null energy condition. Now, these two things together, and using the Einstein equations, we can express the null energy conditions in terms of the function f and g, and that puts a number of inequalities on the blackening factor and the size of the sphere, essentially these two inequalities. Now, for a standard sphere size, which is what people usually consider, g of r is equal to r, it was demonstrated that the transition between the sitter and ADS must be actually hidden behind the horizon. And so it does not give access to the sitter horizon from the boundary perspective. So the type of geometry that people were able to build that do obey these conditions and have a size of the sphere which is proportional to r had usually one boundary and at the sitter horizon, but that is not at the sitter chunk that is hidden behind the Schwarzschild horizon. But anyway, there was not access to the sitter horizon. I mean, roughly speaking, to understand why that's true, roughly speaking, this first condition, what it tells us is that the sphere size must be concave function when walking along the geometry. So as I walk, I do some trajectory along the geometry, the sphere size has to be concave. So it has to first, well, don't remember which one is concave. But essentially, like it has to then say then first increase and then decrease or something like that. Yeah, and then essentially this kind of ruled out the possibility of having a transition between ADS and the sitter, which is not hidden behind the horizon. from the way I'm phrasing this, it should be obvious that there are ways to bypass these no-go theorems. First, in 2D, there is no size of the sphere. So there is no point in asking for monotonicity, and then all these conditions can be easily satisfied. So there is absolutely no problem in embedding the CHEP-th horizon within ADS in 2 dimensions. But more generally, since the condition was actually that the size of the sphere would be a concave function, another thing that you can do is if you want to study the embedding of DSD inside an ADS space, is that you have the size of the sphere in the way it's usually changing in the CHEP-th, and then you would be gluing it not to ADS D, but to ADS2 cross SD minus 2, where you froze the size of the sphere. And in this way, you wouldn't violate the null energy conditions. And that's not a problem, because eventually you should remember that your goal is not to glue ADSD to DSD. Your goal is to study DSD from a holographic perspective, and it's not for you to choose what is the right holographic perspective for DSD. It's that thing that you can glue to it. And so perhaps it's natural. I mean, there are all these statements that the CHEP-th has less degrees of freedom than ADS, etc. So perhaps it's actually natural that it's glued to an ADS2 across SD minus 2 rather than ADSD. Okay, but so that the only point here was that it's okay. This is like you can bypass the no-go theorems in different ways. And here I will essentially focus on the 2D example. Okay. So now what I'm going to do is I'm going to study dilaton gravity theories in the so essentially theories which contain a dilaton field and a metric in 2 dimensions. They have the following action, which consists of the dilaton times the Ricci scalar plus a potential for the dilaton. And this potential, at the moment I leave it free, it's going to be fixed later exactly in order to do the interpolation between the CHEP-th and ADS. And the usual thing is to impose Dirichlet boundary conditions for the dilaton and the induced metric at the boundary, in this case, the ADS boundary. Now, the equations of motion for to the dilaton gravity are essentially, so there is one equation which is the equation of motion for the dilaton, which connects the curvature to the derivative of the dilaton potential. And there is another kind of conservation equation, just an equation over the dilaton, essentially. And now it turns out that you can take these theories, and for whatever potential of the dilaton that you put that is sufficiently smooth, you can construct metrics that solve these equations of motion in the following way. So, metric takes the usual form with the blackening factor. The dilaton is proportional to the radial coordinate, and the blackening factor is nothing else but the integral of the potential. And yeah, okay, I should mention just a few comments. Is that the action that I wrote here is the variation part. The action of 2D gravity also has a topological part, which is fixed by a constant dilaton profile over which you expand, and you can of course also use all these fields to define the thermodynamics associated with horizon. Okay, so now let's consider the following dilaton potential, which essentially is going to have 2 portions. So it's going to be proportional to twice the dilaton for positive values of the dilaton, essentially positive values of the radial coordinate. And it's going to be proportional to minus twice the dilaton for negative values of the dilaton. You remember that the equations of motion were saying that the Ricci scalar is essentially proportional to the derivative of the potential. And so in this case, you can see that the Ricci scalar is piecewise negative outside I will show outside what it means in a second, and positive inside. So it's really a transition between de Sitter space and ADS space. So as I said, the corresponding solution interpolates from a UV ADS boundary to a de Sitter spacetime in the interior infrared that ends at the cosmological horizon. And now if I do a sharp transition, that's not going to really matter. I mean, I can smooth it in some way, but for the calculations that I will show you, it doesn't matter. I might as well just use an absolute value function. So for the sharp transition, the blackening factor also transitions in a sharp way. It will be essentially the de Sitter metric for negative values of this R, and ADS for positive values of R, and that's how the Penrose diagram would look. So it would be, essentially there would be the de Sitter horizon inside, two-sided geometry, and at some point outside the de Sitter horizon, there is a transition and space becomes ADS. So here over this line, the radial coordinate is infinite in absolute value. As you go to the horizon, it decreases, and then at some point it turns into ADS, so it starts increasing again. And it's a two-sided geometry, so as usual, it's dual to some thermophile double like state. And since it's essentially a patched geometry with the head of ADS and the tail of DS, or the other way around, it got the name of centaur geometries. And okay, here I just summarized the thermodynamics of these geometries. So what's the temperature of the horizon? What's the, okay, so here are the flow geometries. So let me just summarize before I start talking about quantum information. So to summarize, there exist solutions of dilaton gravity that embed a part of a de Sitter universe inside an ADS spacetime. They are smooth geometries that have a de Sitter horizon and an ADS boundary. They satisfy the null energy conditions, and now that we have them, we can actually apply the toolkit of standard ADS CHEP-th to study the cosmological horizon. So, I mean, in particular, at the moment, we just constructed these geometries at this point in the talk. So one of the first goals would be to try and characterize what is exactly the dual quantum mechanics. I mean, it can't be exactly SYK. It's probably a deformation, something that looks different in the IR. And so essentially that's what we want to do, is we want to start using tools from quantum information to propose suggestions for what would be the dual quantum mechanics. And that's what I'm going to do using tools from quantum information in the rest of the talk.
Sure, can I ask you a question? Are
Yes,
there
yes,
string
absolutely.
theory embeddings where U phi can be built like this?
No, I think that's not known. So the perspective that is taken here is some sort of ADS-CMT perspective, bottom up. You just construct this geometry, study their symmetries, and etc. I don't think there is a full top-down model where you can build them, but that's an open question.
Okay. Thanks.
Hi, I have one question.
Oh.
So can you go also
yes,
beyond this DS horizon, or do you just on the boundary of the DS by the flow geometry?
Sorry, tell me again. I didn't understand.
Okay, so can you go by this the flow geometry that you have mentioned into the inside of the DS horizon?
Yeah. So in the same way that so you know that in ADS CHEP-th you can probe inside the horizon. There's certain observables that can probe inside the horizon. So for short times, for example, just 2-point functions or the entanglement, and for later times these complexities. I mean, in 2D, many things are all the same because the geodesics, the 2-point functions, and the complexity and everything is kind of for everything the same. But yes, exactly. So the point is that each side is like thermal-like, meaning that if I focus on observables that are one-sided on one of the boundaries, I would just see a specific side. Those won't probe behind the horizon, but as I'm studying observables that involve entanglement between the two sides, this will probe behind the horizon.
Okay, thanks.
All right. So, okay, so that's the third part of my talk is, as I said, to use all the setup to study the de Sitter cosmological horizon, and I will do it indeed from the perspective of computational complexity. So a quick reminder of what is this complexity, or what is holographic complexity. So from the boundary perspective, complexity is a notion from quantum information that measures how hard it is to construct a quantum state from simple elementary operations. So essentially one starts with a reference state and imposes certain gates in an attempt to construct a given target state. And the complexity is essentially the minimum number of gates which is required for this task. Now, in a quantum chaotic system, the complexity is expected to have a certain characteristic behavior, but one typical signature is that the complexity grows linearly for a very long time. So for times which are exponential in the number of degrees of freedom. And there are additional signatures. I'm just going to focus on the linear growth for simplicity at the moment, but additional signatures of complexity in chaotic systems also include a delay of the growth in reaction to perturbation by the scrambling time. That's what's known as the switchback effect. Now, in holography, there are conjectures for what complexity should be dual to, and these conjectures are based on attempts in asymptotically anti-de Sitter space-times, which so these observables have the same behavior as those that I showed in the bottom of the previous slide. So they have a linear growth and a switchback effect. And based on these similarities, they were proposed to be holographic duals of complexity, just to emphasize that these are still conjectures. So the two proposals that got the most attention are, the first one suggested that the complexity is dual to the volume of a maximal slice, which is anchored at the boundary time where the state is defined. And alternatively, a proposal was made which relates the complexity to the action of a diamond-shaped-like region in the bulk, or cone-shaped-like region in the bulk, which is the Wheeler-DeWitt patch, again anchored at the time slice where the state is defined on the boundary. So I'm going to focus on the volume proposal, which essentially says that the complexity is dual to a maximal volume. Of a given state at a given time. And in 2 dimensions, the volume is simply the length of a geodesic, like those that we saw earlier. So that makes things simpler. Now, just going back, so we have it in mind, fresh in mind for the comparison. So for the ADS black hole, I remind you that in 2 dimensions, we saw earlier the geodesics were very simple, kind of straight lines, and their length was growing linearly in time at late times, essentially. It was log of cosh t over 2 beta. Now, these people take to say, well, not only this, but also this, people take to say that black holes are expected to be quantum chaotic systems. But you might ask the same question about the cosmological horizon. So what about the cosmological horizon? Okay, so for this, what we're going to do is use exactly this holographic setup that now we have for the cosmological horizon, and we will just look at geodesics in the center geometries in attempt to study under, again, these conjectures and everything, to study complexity in these centaur geometries, so complexity of the cosmological horizon, of the theory dual to the cosmological horizon. Now, so now the calculation follows very similarly to what we did before. So there is again a conserved momentum. And using this conserved momentum, we can write the length of the geodesics and the time at which the geodesic is anchored at the boundary, and then we can plot them one as a function of the other, or maybe extract them analytically, depending on the case. And the geodesic is simply going to be broken to two portions, one in the ADS part of the geometry and an additional chunk in the DS part of the geometry. So here's a drawing of geodesics. So I start with the simplest one. If I'm anchored at t equals 0, everything is not super symmetric, everything is very symmetric. And so, of course, the geodesics just grows through the bifurcation, no surprise there. As I increase the boundary time, the geodesics start leaning behind the past horizon. So that's unusual. It's not what happens for black holes. And as time increases, the geodesic lean more and more and more and more behind the past horizon until at some point they hit sky plus. So here is a full set of geodesics at different boundary times. And of course, you can identify this element in the sitter interior, which is no other than the diamond that we saw earlier when we just discussed geodesics in the sitter. So this case can be solved completely analytically, and we can give, so the only thing is that it's an expansion for allowed boundary cutoff. We can give the length as a function of time, which is pi plus 2 log, and in this case, instead of a cosh appears a cosine, t over 2 beta. So essentially, this looks quite different from what we see in ADS in the following sense. So first, geodesics, as a consequence of the fact that geodesics in the sitter didn't exist between any 2 points, this projects to the ADS boundary. And so it turns out that geodesics don't exist at all times. They only exist at times which are of order of the inverse temperature. So there will be geodesics, and then at some point these geodesics will become imaginary. It's not very clear how to interpret that from the point of view of complexity of the boundary theory, but just to say that these geodesics stop existing. So perhaps this proposal would have to be adapted after this time. The geodesics never grow linearly with time. So in fact, they even decrease as a function of time. Yeah, so as you can see, so they start with the maximal value, they decrease, and then at some point, which is a time of the order of the inverse temperature, the geodesics essentially hit sky plus and they will stop. At this point, the geodesics are almost null everywhere except at this tip, which is very close to sky plus, so it has a very large contribution of pi. Oh, yes, sorry. So just to emphasize that, I mean, this can be taken in many ways. It's definitely showing that these theories have a very, very different behavior than the one seen in the usual ADS black hole case in 2 dimensions. And the interpretation can be either of different interpretations, either that the complexity proposals have to be changed for this case, or that the theory is not chaotic, or both. But yeah, just to emphasize how different it is in these theories. So this would be like, say, a step in the direction of characterizing, for example, the 2-point functions of the theory on the boundary, or the complexity if you are a fan of the complexity interpretation. All right, now, so now there are different variations that one can do on this setup. The first variation is that you may ask, okay, I glue the specific portion of the sitter, but what if I glue more or less than, in this case, half the sitter to ADS? And this can be achieved very easily. So just change the portion of the sitter that is being glued to ADS. by considering the following dilaton potentials, which essentially are just a shift. So they just kink at a different value of phi naught. So essentially the two geometries are just glued at some different value of the radial coordinate. In this way, they have more or less than half the sitter. So as you can see, in this case, the blackening factor is the sitter for all values of the radial coordinate below a specific value, not 0 in this case, but phi naught, and ADS above this value. And so when phi naught is bigger than 0, we have more than half ds. These are the Euclidean drawings, but when phi naught is 0, it's exactly half of ds. And the upper part is the ADS and the lower part is ds after a Euclidean rotation. When phi naught is negative, it's less than half ds. When phi naught is positive, it's more than half ds that is being glued to the ADS. And there are different limits. So phi naught equals to 0 is the center that we saw before. Phi naught equals to -1 is the case where the transition exactly sticks to the horizon. So there's essentially no portion outside the horizon of the center that is being glued. So it's ADS everywhere outside the horizon and DS everywhere inside the horizon. And the case where you glue almost an entire DS sphere to ADS is a value of phi naught 1 over root 2. In this case, you have an infinitely long ADS throat. And now
I have one question.
Oh yeah, sure.
Can you go back to the previous slide in the picture of the geodesics? Yeah, I mean the previous one.
Yes.
Yeah. So in the picture that you have the horizon, you have taken this RB much greater than 1, right? So what happened
Yes.
in some small RB? So is there any correction to this length? Assume for
yes, absolutely. RB? So you can see. Yeah, so I can. So it's not very pretty. That's why I didn't put it on the slide. But so when is this going to influence? It's going to influence when these two terms are in competition. Oh no, I did okay. I will annotate and then I will figure a way to. Okay. Yeah. So it becomes important when these two terms are in competition. So at times which are very close to pi times beta, so essentially the times very close to this point over here. Because in this point, naively, if you look at this approximation, the cosine is going to go to 0, and that's going to go to -infinity. But that's very obvious that it's not true. I mean, there is a correction here that prevents it from being true. This is because here I was assuming that RB is big, much bigger. And essentially, I can tell you what happens in this limit because you can see it already from the drawing, like it's null everywhere, null, and then here there's a pi contribution. So essentially it goes to, well, you cannot see it, the drawing is a bit chopped, but if you go all the way through, it's going to just stop at pi. So the last one is going to be pi if you actually include all the corrections, just that it's not very nice to look at the full expression. So it's this would be true almost everywhere, and then like a little bit before the end, it will stop being true, and you will have to account for the fact that you have these two terms competing, and you cannot assume that this is extremely large anymore.
Okay.
Hi, can I ask a question?
Yeah. Yes.
Yeah. So, just trying to understand the motivation of this calculations. For example, you mentioned that in de-Sitter we don't have a boundary, and that's why we can't associate, for example, a boundary complexity to a bulk volume, for example, what one does in ADS safety. But in this kind of flow geometry, by looking at this, let's say, by studying these volumes or rather lengths in this two-dimensional geometry, can we understand what we really understand about de-Sitter complexity? Or for example, do we look at the ADS boundary values of the ADS part that you have and the ADS boundary that you have? Do we look at that and do we compute something from there and can talk about DS complexity?
Yeah, so I think, so when you say DS complexity, it should be, what do you mean? You mean that I want the complexity of a theory which is dual to the sitter, right? I mean, because complexity is a boundary quantity.
Yeah.
And so in this case, what you have is a theory which is dual to the sitter in the infrared. So when you go in the infrared, you will have a chunk of the geometry which is the sitter. And so when you study the complexity of this theory, is exactly the question of trying to characterize what are the properties, for example, complexity, quantum information, two-point functions, etc., of a theory which is dual to a geometry which has an infrared portion, which is the sitter.
Thank you.
Right, and at the moment you don't know exactly what is this theorem. You can make some guesses, I will say at the end, because I mean, you know, near the boundary it's just a ADS, so you could expect, you know, an SYK, and there are proposals for, you know, an SYK that is deformed by another SYK, by relevant deformation that is another SYK with some different parameters, or things of this kind, because essentially it's a geometry that near the boundary looks exactly like ADS2, but in the interior it looks different, so it's some deformation of an SYK. And exactly, so the questions that you're asking are essentially questions about this theory and how can I characterize this theory.
Yeah.
So that then once I have characterized it, I can, you know, go both ways. At the moment, I have the geometry, I'm trying to characterize the boundary theory, but once I understand the boundary theory, of course, I can take it back, my knowledge about everything. I don't know, there are things, the units are evolving in some way, all the advantages that you get from the usual duality you would be able to get, or that's the hope, at least that's the long-term goal.
Yeah, so again, for example, if we really are able to characterize the boundary theory corresponding to this flow geometry, we would expect something which again would, for example, in the region where it is ADS is supposed to show us something like a SYK kind of behavior, and inside the region where the theory looks like a de-sitter, in that region you expect the behavior of that quantum system to be the dual of the de-sitter geometry, right?
Yes.
Okay. Thanks.
All right.
Just to clarify one more point. So is this RB is related to some sort of entropy, because we expect this length to relate some kind of entropy in, like, right?
The RB is just essentially the cutoff. It's the 1/delta or something like that you usually have. I mean, yeah, it is. Let me see. I mean, it's not. So I know what you're saying. You think that RB, because it's related to phi b, it is the value of the dilaton, it will be related to an entropy. I mean, the leading component in the entropy is actually the zeroth order, the phi naught. But yeah, it's true that the variation would be phi b. So it is true that it would be somehow related to the variation of the dilaton.
Okay. Thanks.
All right. So, okay. So then we are now with the more or less than half ds, and okay, and things are quite similar. So for more or less than half ds, you can see the drawings over here. This is less than half ds. This is more than half ds. And essentially, there are different geodesics. And as you will see, things behave extremely similarly. There are some differences for specific ranges of phi naught, negative phi naught. So for cases with less than half ds, actually, for several boundary times, there are competing geodesics. So several geodesics locally of maximal length, which compete with each other. And okay, if we keep taking very seriously the complexity proposal, we should take the maximal one out of all of them. But here is just the drawing of the coagulation of geodesics. So you see that when we have more than half ds, we have the full diamond here happening inside the ds. And when we have less than half ds, we have kind of chunks of these diamonds. All right. Okay, and then we can draw the length of the geodesics. That's the V of t, is the length of the geodesic as a function of time. And as you can see, they are quite similar. So the red is the centaur, the green is the more than half ds, and the yellow and blue are the less than half ds. And as you can see, almost always, instead of increasing, the complexity simply decreases and stops existing at some time of the order of the inverse temperature. The blue, the funny behavior in the blue is exactly this kind of competing geodesics, that for a given time we have more than one geodesic that is competing, and we should select the maximal one. But in any event, this behavior at some point kind of disappears, and in favor of this kind of decrease again. So as you can see, the volume as a function of time does not grow for a long time. And the last thing that we did was we said, okay, but these geometries are a bit funny. We interpolate between two geometries. So maybe this is some kind of thickness of the interpolation. And to rule that out, we actually considered float geometries between two ADS spaces. Meaning that we would glue an ADS with a certain curvature scale to an ADS with another curvature scale. And this is also done by having a potential which jumps, has a curvature of 2 over here, and then 2 plus alpha at above a certain radius and below a certain radius. So these are float geometries, but that are essentially an ADS black hole inside another ADS of a different curvature radius. But indeed, in this case, you have linear growth with the expected slope that is coming from the interior. So you can see that this funny behavior that we are seeing of the geodesics or of the complexity is not actually a result of the interpolation. So just to summarize, or at least this is maybe this is a bit of a strong statement, but one possible interpretation would be that the behavior of the cosmological horizon is not chaotic. An alternative interpretation would be that the complexity proposal would have to be adapted. This is not a consequence of gluing it to ADS, but a consequence of the interior not growing linearly with time. Anchoring we are doing this in a very organized way with the ADS boundary, etc. But there are several proposals due to Saskin and Shagulian, and actually very recently also Rob, of studying complexity in the de Sitter space, focusing only on the de Sitter part, but anchoring the geodesics on the stretched horizon. And they see similar features. So they see exactly the geodesics hitting Sky Plus, disappearing at a certain time, etc. And I think, well, that it's not extremely well understood yet what this is. There are different interpretations for that. Yeah, so let me comment on what kind of microscopic theory will give this type of behavior. So this is going to be after the summary. So I'm going to summarize and give a little bit of a hint of what one should do to construct a microscopic theory that has this behavior. So just to summarize first, we saw that it is a challenge to study the cosmological horizon holographically, but it can be done by constructing float geometries that have an ADS boundary and the de Sitter interior. This gives a framework to probe the cosmological horizon, and we studied complexity in these geometries and demonstrated that the behavior exhibited is not chaotic. Okay. Again, or that the complexity proposals would have to be amended or changed. So what are the open questions? So the first open question is that the interpretation, so first thing that you have noticed is that the interpretation as complexity seems to be somewhat shaky because the geodesics stop existing at some time. So what happens to the complexity after this time? That's an open question that I think we don't understand yet. The question can be equally phrased on two-point functions in 2 dimensions. Some other things that you can do to try and characterize these geometries is, for example, study them in different dimensions, or ask how does the geodesic length react to perturbation, all the story of the shock waves and the switchback, etc. And that's my final comment on what is the boundary dual. So we know that near the boundary, we have nearly ADS2, so that would be like an SYK in the UV. And in the IR, there is a different behavior, which is the theta. So essentially what we expect is to have an Archie flow from an SYK model by turning a relevant deformation to an SYK. And one proposal that was made in this paper is that perhaps you can use an SYK with a different value of the number of fermions that interact in each term of the Hamiltonian. And they were seeing some kind of supporting evidence for that in the behavior of the heat capacity, etc. Right, so essentially, just to highlight, eventually the final goal would be to build a microscopic theory which is dual to the Sitter space. And yeah, and I hope that we are doing some steps in this direction. Yeah, that's it. So thanks.
Thank you, Shira, for the nice talk. So we can have a few questions now. So let me ask one question. So as you said that this cosmological horizon is not chaotic, that means from the boundary you can also probe that using some kind of what should I say, OTOC or something kind of behavior, whether this is chaotic or not. Is that true? I mean
yes. So yeah, right. So the OTOC has been computed. Actually, in one of the previous papers, the first ones, those that suggested the geometry, I think from Diego Hoffman and Dio Aninos, and they found that the OTOC wasn't decaying or wasn't behaving in the way which would indicate chaos. So that's another support to the claim that the theory is not chaotic. So we have more reasons to believe that the theory is not chaotic, not just the behavior of these geodesics. It seems to be an indication in the same direction.
Hi, sorry, could you go back to the slide where you had the geodesics for the inside as well as the outside region, the diamond-like and the...
This? Oh.
Yeah, maybe the previous 2 or 3 slides before this. Yeah, this one. So in this one, the non-trivial part, the pi part comes from the diamond, right? The middle part, which is the usual diamond-like structure in DS geometries. And the rest of the things are coming from the outside regions, which are ADS boundaries. But these non-trivial parts also behave differently from that of the usual ADS safety or usual ADS geometries. So that's what is resulting in this non-trivial behavior of not really linear growth, but going up and coming down. But how does the information of these holographic flow geometries go into this term, the second term of your LT? Exactly.
Yeah, right. So, I mean, you should remember that you are comparing this not to a constant. I mean, this pi, essentially, what are you comparing it to? You're not comparing it to another constant, right? You're comparing this to the black hole. Usually in the black hole, from the interior, you have a linear growth, right? From the slices that go like this or something like that. Mm-hmm. And here you see that in contrast, I mean, it's true, you also have this thing coming from the boundary, but just to say, you see the fact that it's a constant is already very, very different from what happens in the black hole, because usually this linear growth is coming from the interior in the black hole. And here you don't see, you see kind of a constant. So already the fact that it's pi and it's a constant from the interior is telling you that something is very different is happening in the interior of the geometry.
Yes.
Like the volume behind the horizon is not growing. I mean, of course, the volume behind the horizon is not a very well-defined until you define a foliation. It can be defined in different ways, but I should say that it's not linearly growing, at least not in 2 dimensions.
Oh, so you're saying that the interior region, the difference of the interior region making the difference in these plots as well. not the
Right.
outside ADS parts that much.
Right. That it's already striking that the interior is so different.
Mhm. Okay. Thanks.
I have just one more clarification. So very naively, what comes in the mind that you have considered the complexity volume proposal. So maybe this one can also probe these visited things using these other complexity proposals, or is it something that this is proposal dependent thing? I mean, for example, CA.
So we haven't tried. I think that's very interesting, and maybe I can point out in this context that so even if you don't go to the action, I mean, the action has some subtleties in 2D, you have to add some special boundary terms and stuff, but Rob had a paper quite recently that was named something like complexity equals anything or everything or something like that. And he was suggesting that actually in ADS, the volume was not unique, that you could, instead of integrating just, the induced metric on the surface, you could integrate a bunch of like other kind of curvature invariants. And they would all have in ADS the same behavior, like linear growth and reaction to shocks. So this, I think, would be very easy to borrow and implement in this setup. Or I'm not sure if you could integrate something else different along the surface. Perhaps that's interesting. Just to see, how is this influenced by changing, like slight adaptations of the proposals. Maybe in these cases, if you minimize something different, maybe, I mean, even by minimizing something different, you might be able then to reach later times, because the fact that they stop existing is dependent on the functional being externalized.
Right. Thanks. So if we don't have any more questions, maybe let's thank Shira again. And thanks for giving the talk, and thanks for agreeing.
Yeah, no problem. Thanks for
Stop.
yeah.